Okay, so we'll look at a few examples of the binomial and geometric distributions. So recall that a binomial setting, you have two outcomes, success or failure. We have a fixed number of trials. Trials are independent, and the probability of success is the same for each. We took a look at Plinko, so you drop the Plinko chip in, there it goes, and it's binomial because as it hits each peg, there's two outcomes, left or right. Each time you drop a chip in, it'll hit 6 pegs, so there's 6 trials regardless of the path, and each time it hits a peg, it's independent. And then that fourth one, the probability of success, right? So if we define success as a right turn, so it's always going to be a 50% chance that it turns to the right. So what we're going to do is extend what we've been doing in class, or what we've been learning about these probability settings, and we can create those probability charts, those probability distributions for something like this, even though it's a bigger sample. So we'll define x as the number of times the chip will fall to the right, and there are 7 possible outcomes. It could go to the right 0 times, right? So 0, that'd be left, 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 right? 1, it could be right, left, 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 left. It could be left, then a right, then a bunch of lefts, so on and so forth. And so what we need to figure out in order to come up with our distribution is how many ways each of these can happen. So like I just said, there's one way, right? There's one way to get 0 right turns. There's one way to get 6 right turns. If we start doing just like we've done up to this point, we can start listing them out, right? But the issue here, right, we've got 6 ways here. As we start to look at 2 right turns, it gets a little bit more complex, right? Right, right, and then a bunch of lefts. Well, there's a lot of ways we could come up with 2 rights and 4 lefts. Left, left, right, right, left, left. Even if we're really, really organized with how we're doing this, there's going to be a lot of combinations, so we need something different. This is where combinations can come into play. So for us, this NCR, it's under your math function in your calculator, and if you go over to probability, you'll see NCR. And what we're looking at, N is the total number of trials. So right there were 6 different pegs, and R will be our number of successes. So for 0 successes, and remember for us, we said a right turn was our success. So how many ways were there to get 0 right turns? So this is saying out of 6 bounces, 0 right turns. We saw that was all lefts, so there was one way to do that. All right. Out of 6 bounces, how do we get, how many different times or ways can we get 1 right turn? We can actually list those by hand. It's not that bad. But when we got to 2 all of a sudden, right, out of 6 pegs, that 2 of them are right, right? So, you know, right, right, left, 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 you know, right, left, left, right, left, 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 right, left, left, right, right. There's a ton of these combinations. Well, this NCR will tell us that there are 15 combinations, right? So there are 15 combinations of 2 rights, and so that would leave us with 4 left turns. And we can keep going through here and realize that there are 20 ways to come up with 3 lefts and 3 rights, 15 ways to come up with 4 rights and 2 lefts, 6 ways to come up with 5 rights and 1 left, and then 1 way to get all rights. Right? If we had to go all right, there's only 1 way to do that. Right, 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 right. There's only 1 possible combination of 6 R's. So what we're going to do with that then is, if we take a look, so here's one particular example of each. So there was only 1 way to do that. And we just saw there's 6 ways to rearrange those letters, right? That's one of the particular combinations of 2 R's and 4 L's, but there's 15 different ones we could come up with. There's 20 ways we could combine 3 R's, and 3 L's, and then 15, 6, and 1. Now, the individual probability of each one of those, right? 5 left turns will be 0.5, 0.5, 0.5, 0.5 to the sixth. Here, we'd have 0.5, there's 1 right turn, and then 5 left turns. Here we've got the probability of right is 0.5. There are 2 of those. And the probability of left is 0.5. It just so happens that it's equal probabilities. And then here it's 0.5 to the third, 0.5 to the third because we have 3 of each. Here we have 4 right turns, 2 left turns, 5 right turns, 1 left turn, and then all 6 are right turns. One thing that we should realize, if you look at those exponents, all of those exponents, when you sum them together, 6, 1 plus 5, 2 plus 4, 3 plus 3, 4 plus 2, they all add up to 6, the total number of outcomes. That's important. The other thing to realize is as the number of rights goes up, right, and we go from 1 to 2, 3, 4, 5, you'll notice the number of lefts, 5, 4, 3, 2, 1, is dropping. And so, whereas we usually don't have this middle part in here, this is just kind of showing you where all the work's coming from. But total probability, there's one way to get those 6 left, or 6 left turns, yes. There are 6 ways to combine 1 right turn with 5 left turns, right? And so those probabilities, 0.0156, 0.0937, 0.234, 0.312, 0.234, and again, this would be 15. There are 15 ways to come up with 4 R's and 2 L's. Right, there are 15 combinations of those particular letters. And then, so 0.0937 and then 0.0156. So again, typically we don't put this middle section. Right? Typically we wouldn't show all this work in our table. We typically just have x and the probability of x, which is what you see right here, right? X was the number of right turns. And so we typically just have this table. Previous page just shows you how each of them work out. So suppose we drop 5 chips into the board. What's the probability that we land over here in slot D? Well, the trick here is to realize how many right turns would it take to get into D? Well, first off, if you took 0 right turns, if it stayed left, 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 well, that would put you into A. So this is really slot A. 1 right turn anywhere along the way would actually put you in B. 2 right turns would get you to C, so on and so forth. So if we did 3 right turns, right, and we did take a look at this in class, regardless if you did 3 right turns, so right, a right, 3, and then 1, 2, 3, you'd get to D. And no matter which way you do it, if you do a left, 2 lefts, and then 2 rights, and then a right, and then a left, there we are right back in D. So as long as we have 3 rights, we're going to get to D. So the probability that we land in D is 0.312. So the probability that 5 chips in a row, right? The probability of 5 chips in a row landing in D, D and D and D and D and D, well, 0.312 to the 5th, which is 0.003. So not very likely that we land in the center slot every time that we drop one of our 5 chips. You know, another way we could use our table, find the probability that of the chips that we drop in, the 1st and 5th land in D. So we have D. So then in the middle, excuse me, it's not D, not D, not D. So we know that the probability of D is 0.312. And then we're going to end at 0.312. Excuse me. So the probability of not D would be 1 minus 0.312, 0.688. And then when we put all that together, multiply it all out, it's 0.3 0.0317. So there's about a 3% chance of the first and last one landing in the middle, and then the three chips in the middle, the three chips that we drop in the middle there, they land somewhere on the outside. So typically, though, if you've ever seen Plinko, they don't have A, B, C, D, E, F, G on the bottom. They have monetary values. So what we're going to do is just, we're going to let X equal their winnings. So if we do it that way, the probabilities aren't going to change down here at the bottom. But what we can do is extend what we were doing before and come up with an expected value. So when we drop five, well, it says balls, should be chips. We drop 5 chips in. To come up with the expected winning for one ball, remember we have a formula for that where we go, x1 times its probability, x2 times its probability, and then we sum all those together. The other option is list 1 and list 2. And remember, when you tell your calculator that you're going to do this, the list 2 is your frequency list. So the expected value there, 33, 27, 66. So that's for one ball, or one chip, if you will. And then if we drop all 5 of those chips in, really what you're doing is a chip and a chip, and then another chip, plus another chip, plus another chip. So it's 5 unique chips. So 33, 27, 66 plus 33, 27, 66. Well, there are 5 of those. So really, we could have just multiplied those together. 5 times 33, 27, 66. So if someone plays Plinko, their expected winnings, $16,638.30. Not a bad day's work right there. So another example, maybe we go one where it's not a 50-50 shot. Suppose you received a shipment of 5 monkey scooters. Of course, right, we've shaved the monkeys, we've got them typing on the calculator, so now we'll give them a scooter, let them kill some time, keep them happy. 15% of those aren't working, or there's a 15% chance it doesn't work. So what's the probability 3 or more scooters in a shipment that you just received are defective? So why is it binomial? Well, first things first, there's 2 possible outcomes, right? They either work or they don't. There's the first thing. The next, we've got a set number of trials, right? We have 5 scooters that we're going to try. Each scooter is independent. As you get them out of the box, one's not going to affect the next. And the probability that they're defective isn't changing. It's always going to be 0.15. A couple other quick notes. So the probability that it doesn't work. So we have probability that a defective scooter is 0.15. Well, that means that the probability of not defective equals 0.85. And so in order to do this question, what's the probability 3 or more, we're going to go ahead and come up with our distribution table. And so we'll set x as the number of defects. Right? So first things first, how many ways can we come up with? Again, x equals number of defective. Right? So how many ways can we get 0 defective? 5 choose 0. There's one way. They all work, right? That would be not defective, not defective, not defective, not defective, not defective. Right? How many ways can we get 1 defective? In other words, 1D and the rest are not Ds. Well, there's 5 combinations of that. Here's where it starts to get a little bit more interesting. We don't want to have to write all these out by hand. So this would be, again, this is 5. We're going to take 2 at a time. So there are 10 ways to get, right, 2 Ds and then 3 not Ds. There are 10 combinations of those letters, so on and so forth. And so what's going to make this different than the problem we just did are these probabilities are going to change. So what's the probability that we get something that does work, right? Not defective, not defective, not defective, not defective, not defective. Well, that would be 0.85, and there's 5 of those. Right? Here, you can see there are 4, right? There are 4 not Ds, right? And again, the probability of not D was 0.85. So we have 4 not Ds and then 1 defective, right? The next one down. There are 3 not Ds, right? There are 3 not Ds, so we put 3 that aren't working, or that aren't defective, excuse me. And then there are 2 Ds, right? And remember, the probability that we had a defective was 0.15, so we have 2 0.15s. The next one down, 3 that don't work. Again, so if you think about this, this would be um, defective, 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 not, not. So there are 2 not defectives. There's where the 2 there. There are 3 that are defective, which is why we have the 3 there. 4 that are defective. So that's 4 Ds, 1 not D. As you can see, what's happening is the numerator associated with each of the probabilities is associated with the number of Ds or not Ds. And then finally, so to get the total probabilities, we take the total number of ways that we can come up with each of those. So this would be this first one, right? There is one way to come up with 5 working scooters. There are 5 ways, so this would be 5 times 0.0783, 0.3. So the probability that we get one defective scooter, 0.3915. The next one, 0.138, so 10 times 0.0138. There are 10 ways to get this particular, right? There are 10 ways to get that combination, 10 times 0.0138, so on and so forth. So what we're interested in, right, the probability of 3 or more, so that x is greater than or equal to 3. We got the table, so just go grab it. Add them up. Probability 0.0267.